Ngalakin Khadijan Nyunga Boja.
Hello everyone, welcome to the first lecture of the ELEC 4404 Signal Processing. From this week until week 3, we are going to use 3 weeks time to introduce the first chapter of your unit reader, which is the random variable. The content introduced in the first chapter will be very important for your future study. For instance, when we move on to the chapter 2, random process, in week 4, we are going to use a large number of concepts, properties, formulas learned from the chapter 1. So learning the first chapter well will be an important step for your future study. The discussion of the chapter 1 will be divided into 3 parts. And in this week, our target is to finish the part 1. In the part 1, we have 4 sections to introduce. The first section is about the concept of random variable. In the section 2, 2 important tools which will be used to fully describe a random variable will be studied. And in the section 3, we are going to learn some extensions to the 2 tools we learned from the section 2. By the end, in the section 4, we are going to introduce 6 important distributions, and then use the tools we learned from the section 2 and section 3 to analyze these 6 distributions. Now let's start our first lecture. First of all, we are going to study what is a random variable. From this slide, you can see a random variable is defined as a function. This function specifies the relationship between 2 things. One thing is an uncertain experiment outcome zeta, and the other thing is an associated number x zeta. Now let's put all these components into a graph so we can see the relationship between different components. First of all, we need one experiment. This experiment is a general term which refers to any real-world practical operations. For instance, playing a poker card, rolling a dice, or the conduction of any physical experiment. They all can be referred to these experiments. And these experiments should be able to produce some outcomes. And we put all the outcomes into this big circle. Let's use the zeta to denote the outcome. So we have the zeta 1, zeta 2, and so on. Next, a function x is given. This x is using the experiment outcome as input parameter. And then to produce the corresponding function values. So we call these the values as the numbers or associated numbers. These numbers are actually the function values associated with the input parameter zeta. In this graph, the random variable is this x function. So I'm writing RV as the notation of the random variable in short. But under what kind of situation we can use a random variable to analyze the system? The only condition is, so regarding the given experiment, we must be able to know the collection of all the possible outcomes. But in the meantime, we are not able to predict exactly what will be the outcome of a particular experiment trail. That means I know what will be the result, but I don't know what will be the result of this trail. In such situation, we have to use the random variable to analyze this system. The next concept is about space S. Space S is defined to be the collection of all experiment outcomes. So in our graph, the space S is given here, which contains all the possible outcomes from that experiment. E1 to E is defined as subset of the space. So again, let's make one example. E1 equals the set which contains the zeta1 only. So in this case, you can see, first of all, zeta1 is one element of E1. In the meantime, zeta1 is also the element of the space S. So we can say E1 is a valid subset of the space S, and E1, as a result, is a valid E1. Please also be reminded, so all the E1s must have a probability associated with it. So in other words, we are using this way to denote the probability associated to the E1. Of course, depends on different experiment. The result will be different. The probability will be different. So we just give the notation here. Finally, in this slide at the bottom, you can see we are introducing different types of the random variable. A random variable is called discrete if the values of the random variable function is countable. But if the possible values of a random variable function is infinite, cannot be counted, so we call this random variable as continuous random variable. Now we have already understood the concepts associated with random variable. Let's using a couple of axes to go through them. First example, a player rolls a dice to gain bonus. He is allowed to play this game once only, and the bonus money will be $100 each point he gets. So first of all, what is the experiment in this case? Of course, rolling a dice is the experiment. And what will be the outcome of this experiment? Let's use the point on the face towards up as the outcome of this dice game. If we assume the dice is a regular dice, is a fair dice, which have 6 faces on it, so the total number of the possible outcomes for this game will be 6, because there are only 6 faces on this dice. And the outcomes will be, so I just write them on the slides. Zeta1 is 1, this means 1 point on the face towards up after you roll the dice. Zeta2 will be 2 points, Zeta3 will be 3 points, Zeta4, 4. Only 6 possibilities as the 6 outcomes from this particular experiment. Next one, what is the space? We know the space S is defined as the collection of all the possible outcomes. So in this case, space S is the collection or a set of all the outcomes from this game. Could you list the 3 E1s and their probabilities? Yes, we can. E1. Just make whole question easier, okay? E1 is a very simple case which contains only one outcome, Z1, in its set. Again, you can see the Z1 is the only element in E1, and Z1 is also the element in the space S. So that means E1 is a valid subset of S. So we can say E1 is one event. And the probability associated with E1, this event, is equal to, because there's only one single outcome, Z1, in the set of E1, so the probability of E1 is equal to the probability of the Z1, which is equal to 1/6. Now we assume the dice is a fair dice. Okay. Another example, E2 equals, this time, let's assume there are two outcomes contained in this event. Now the probability of the E2 event is equal to, because in this case, we have two outcomes contained in the event E2. So the probability of the E2 event should be the summation of the probabilities of the two outcomes. Which is equal to, so 1/6 plus 1/6 is 1/3. If you want one more example, you can just do it by yourself. So like this. So I just give the result. So I think this is just the exact same idea as what we have gone through. We just need to save some time in the lecture, okay? Finally, the very last question. Can you define a random variable? Yes, we can. But what will be the random variable of this case? As we mentioned in the previous slide, a random variable should be a function which can be used to map the experiment outcomes to the corresponding values. For this question here, we have already got all the possible outcomes from this rolling dice game, and the corresponding values returned by this random variable function will be the bonus money. So in this case here, the random variable x, which use the theta as the input parameter, will return us the amount of the bonus money. And the question is saying the bonus is $100 each point the player gets. So we got 100 theta. Now this is our random variable for this question. What are the possible values of this random variable? Okay, that should be very simple, but anyway, we just use a small table to show us this result. The first column is just the outcome of the experiment. The second column is the return value. In other words, the value of the random variable. There are 6 possible outcomes. We just list all of them out. The corresponding bonus money or the random variable values are 100, 200, up to 600. So now for this very last question here, these green numbers are the possible values of the random variable. Before we move on to the next question, I want to ask one more thing. What is the type of this random variable? Can you recall how we define the type of the random variable? If a random variable is a discrete type random variable, if the values of the random variable are countable, if the number of the values of the random variable are uncountable, that variable will be the continuous type random variable. In this question here, In the second column of the table, we can see the total number of the possible values of the random variable is 6, which is countable. So this is one discrete random variable. In the next slide, you can see a summarized result regarding this example. If you think there's anything unclear from my explanation, you may refer to this slide to understand how we derive the result. Next question. In an experiment, a coin is tossed 3 times, and the sequence of heads and tails is noted. Let's use H and T to denote the head and tail of the coin. So which of the following space S is the correct answer for this question? I think the first option we need to rule out is the option C. C option is saying the space S of this experiment depends on the outcomes of the 3 tosses. I think the problem is with the depends on. We have mentioned the space of an experiment should be the collection of all the possible outcomes. It doesn't depend on any particular outcome of a trio experiment. So this depends on is incorrect. So C is ruled out first. Between A and B, A is not the correct answer. We said in this game, a coin is tossed 3 times and the result is recorded. So in other words, in the result of each trio experiment, it should contain 3 head or tail results regarding the coin tossing. But in the A, you can see it contains only 2 outcomes in the space, and each outcome contains only 1 head or 1 tail. This doesn't make sense. It's totally wrong. So A is ruled out as well. So the correct answer for this question is the B. Okay, the very last question here regarding this concept. We have got a bag and we put 3 balls into the bag. These 3 balls contains 1 white and 2 black balls. And we are going to pick up 2 balls randomly from this bag. So what will be the space? So for this game, in each trio experiment, the outcome should contain the color of 2 balls because you are going to pick up 2 balls randomly from this bag, not 1 ball. So out of the 4 options, if the option contains only 1 single color, that must be wrong because you are going to pick up 2 balls, not 1. So based on this, we know the option A, C, and D are all incorrect because they are using 1 single color to indicate the result or outcome of this game. Now the only one left is the option B. Okay. Now this is just our discussion regarding the concept of the random variable. Now we have done this first section, and in the next section we are going to introduce 2 important tools. But before that, we need to understand why do we need 2 tools to fully describe the random variable. Let's go back to our first slide here. So remember this one, this graph? So we mentioned regarding the random variable, we have a group of the outcomes coming from the experiment. We have a group of the numbers or values associated with these outcomes. Is that enough to use this group of function values to fully describe a random variable? The answer is no. And for explaining this, we need to understand the outcomes from that experiment are not certain. As I mentioned, we are not able to predict what will be the result of a trio experiment. So if we just mention the values of the random variable function, we are missing the information associated with this probability. So for this issue, if you want to fully describe a random variable, we must need two parts of the information. The first part must be the values of the random variable function. The other part of the information are the probabilities associated with these values. Because of that, so we must have some tools to help us to combine these two group information together. Now, we come to the section 2 and start to introduce these two tools. The first tool we are going to use is called cumulative distribution function, or you can call that as a CDF in short. Regarding the notation of the CDF function, we always use the capital F to denote it. Capital F followed by the name of a random variable. So in this slide, you can see we are writing the capital F here and followed by capital X as the subscript. This means we want to evaluate the cumulative distribution function for the random variable capital X. The lower x in the brackets is just a general parameter for this function. Typically, the range of the lower x covers from positive infinity up to negative infinity up to positive infinity, the full range. How we define the cumulative distribution function? So in the next slide, you can see the mathematical formula defining this cumulative distribution function. We define the CDF function of x as a probability evaluation. This probability is the probability of the event that x is smaller or equal to the given parameter lower x. This event implies a subset of space S, which consists of all outcomes zeta, so that the x zeta is smaller or equal to the given parameter x. For helping us to understand this definition, let's just recall that rolling dice game. For that rolling dice game, beside I used a barrel corner here, we have the outcomes, we have the function values or random variable values. 1, 2, 3, 5, 6. And the bonus money as the function values, like this. Now, if you want to evaluate what is the CDF function of the random variable x, this random variable x is the same as the random variable we introduced in that rolling dice game. And the parameter is just x, but for this question, temporarily, let's give this parameter x a value. We assume x equal to 300. In other words, we are currently evaluating the CDF function value at a particular point where x equal to 300. Based on this definition given in the slide, this CDF function can be translated to the evaluation of the probability of the event where the random variable x value is smaller or equal to the given parameter 300. Now we can just move to the small table. In the second column, we have got all the possible values of this random variable. We just need to pick up the ones which can satisfy this condition. So now you can see in the first, second, and third rows, the random variable values are all lower or equal to 300. So the first 3 rows are valid rows. Now let's go back to the slide. You can see, so this event implies a subset of space S, which consists of the zeta such that this condition can be satisfied. So in other words, out of the first three valid rows, we are going to find the corresponding outcomes, which are the Z1, Z2, Z3. And these three valid outcomes comprise a subset of the space S. They are the event for this situation. And the calculation should be pretty simple, which is equal to P Z1 plus the probability of the Z2 plus the probability of the Z3. Result is 1 over 2. So pretty simple calculation. But this can help us to understand the situation we expand here. In other words, let's just clear up this section. We said the evaluation of the cumulative distribution function is actually evaluation of the probability of the event. This event is actually a subset of the space S. And this subset contains some outcomes which can satisfy the condition specified here. Okay. Before moving on, so just one more thing we need to notice. I mentioned the cumulative distribution function is actually the evaluation of the probability of some events. No matter what events are evaluated here, the result must be the probability. For the probabilities, the maximum value must be 1, the minimum value must be 0. So in other words, for the cumulative distribution functions, its maximum value must be 1, its minimum value must be 0. At the bottom of the slide, you can see 3 examples. They are all CDF functions of some random variables. The shape of them are not the same, but the minimum and the maximum values of all these 3 CDFs are between 1 and 0. So here, the maximum value is 1, 1, and 1. The minimum value 0, 0, 0 for all 3 cases. Okay, so this is the first important property of the CDF function. By the way, there's one more question left at the bottom of the slide. So please think, what is the probability of the event that the random variable x value is greater than the given parameter low x? For this question here, we can just do a very simple transition. So such probability is actually equal to 1 minus the probability that the random variable x is smaller or equal to the given parameter rho x. But the later part of this term is actually the definition of the cumulative distribution function of the random variable x. So this is equal to 1 minus f x. Then solved. Okay, let's move on. A short example. Actually, we have already explained this example by using that table in the previous slide. So now you just skip it and move on to the next part. Okay. Now in the new slide here, we are going to introduce 2 cases and then compare the result to derive one more property of the cumulative distribution function. In the first case, in both cases actually, we are using that rolling dice game as an example. And in the first case here, the parameter used in the cumulative distribution function is 300. And in the second case, that parameter is increased from 300 to 500. And for the first case, I don't think we need to just explain it too much because we just finished this example. Okay, and let's move on to the second case where the parameter used in the CDF function is 500. When we increase the parameter of the CDF function from 300 to 500. And we need to change the number of the outcomes included in the event, because there are 2 more entries in the table which can satisfy this condition. So for the new event, in addition to the Z1, Z2, and Z3, we need to include the Z4 and Z5. And the probability will be changed accordingly. Now let's go back to the result. I have done this calculation. So when the x2 equal to 500, the event E2 will contain 1 point, 2 point, 3 point. So Z1, Z2, Z3, and Z4, Z5. And the probability of this new event E2 will be equal to the summation of the probabilities of all 5 outcomes, which equals 5/6. So in other words, the CDF function for the x2 equal to 500 case should be equal to 5/6. If you compare these 2 values for these 2 cases, so when the x1 equal to 300, our CDF function value is 1/2. When the x2 is 500, which is greater than x1 equal to 300, our CDF function value is increased from 1/2 to 5/6. This is indicating if the x1 is smaller than x2. First of all, the event E1 is a subset of E2. And the CDF function value for x1 is lower or equal to the CDF function value of the x2. Okay, if this is still not clear, let's just do a graphical repetition. Okay, we define the I space is given here, which contains Z1, Z2, Z3, Z4, Z5, and Z6, the 6 outcomes. And when the X parameter is equal to 300, we know the event E1 will contain only these 3 elements inside. So this is our E1 event. When we increase the parameter from 300 to 500, and now we got another event. This is E2 event. Graphically, you can see E1 contains less element than E2. And E2 contains all the elements of E1 and then plus the Z4 and Z5. So we can say E1 is a subset of E2. And when you evaluate the probability of these 2 events, because E1 contains less elements than the E2, so the probability gets less. So we can say the probability of E1 event is smaller than the probability of the E2 event. Sometimes E1 may contain exactly the same element with E2. In such case, these 2 probabilities will be equal. As a result, we can see this result. Okay, this is the second important property. Let's just make the conclusion. If x1 is x2, so in other words, if you increase the value of the parameter of the CDF function, so the CDF function value will be remaining the same or going up. So this is saying the cumulative distribution function is a non-decreasing function. You may say in one day, okay, I got my CDF function, looks like, okay, this one. Okay, I suppose this is right. If you say, okay, my CDF function looks like, the shape of that looks like this, it should be okay as well, because it's just going up or remains the same at some steps. But if you tell me in one day, okay, my CDF function looks like this shape. Sad to say, this must be incorrect. Because in this small section, when we increase the x value from x1 to x2, your CDF function value is decreasing. But CDF function should be non-decreasing function, so this must be wrong. Okay. Next, let's see the next property. We have already known for two given parameters x1 and x2, you got two corresponding CDF function values. So in the diagram, in the graph given at the bottom of this slide, you can see we have the x1 given here, x2 given here. Based on these two parameters, we are able to find out the corresponding fx(x1) and fx(x2). The difference between these two CDF function values are this red color segment, which is fx(x2) minus fx(x1). So this just indicates what is the difference between these two function values when we use different parameter values x1 and x2. Physically, the size of this small red color segment is indicating the probability that the random variable capital X value fall in between x1 and x2. So here we are showing this explanation in mathematical way. The difference between the CDF function value is indicating the probability of the event where the random variable capital X value is falling in between x1 and x2. Next one. Similar story, okay? You used to have the x1 and x2, but the special condition is if the fx(x2) equal to 0, and x1 is smaller than x2, this is known before. So what will be the result of the CDF function value for x1? That will be 0 as well. This should be a very straightforward result, but anyway, we just go through that. First of all, we know that x1 is smaller than x2. Based on our analysis in the previous slide, we know that fx(x1) must be smaller or equal to the fx(x2). And based on this new condition, we have already known for the x2 input parameter, the CDF function value is equal to 0. That means the CDF function value for the x1 input must be smaller or equal to 0. But this CDF function must be between 0 and 1. It's impossible to get a value smaller than 0. So the only possible value for this fx(x1) must be 0 only. Okay, this is how we derive this property, so easy one. And in this page here, we are summarizing all the properties regarding the cumulative distribution function together. I don't think I have to go through it again, so please just make sure you understand these properties and know how to use them. Okay, let's move on. There's a y-axis, small testing to see if you have understood the concept of the CDF function and the properties. In this question here, the CDF function of a random variable x is given. What is the probability of the event? So this is the whole question. So I'd like to draw this CDF function for our analysis. The horizontal axis should be just x value, starting from negative infinity to positive infinity. And this x direction, the axis, will be divided into 4 sections. The first section starts from negative infinity up to -1. And the second one is from -1 to 0, and then 0 to 1, and 1 to positive infinity. When the x is between negative infinity to -1, the CDF function value is 0, so remains at 0. Between -1 to 0, the CDF function value is changed to 0.5. The height is 0.5. And from 0 to 1, so we start to linearly increase the value for the CDF function. So when the x is 0, x is 0, 0 plus 1 is 1, 1 over 2 is 2, so it's half. So this is start point. When the x is 1, 1 plus 1 is 2, 2 divided by 2 is 1. So the end point here should be at 1. Between this start and the end points, we linearly increasing the function value. By the end, in the very last segment, so the function value remains at 1 constantly, like this. Okay, this is the CDF function curve for this random variable. The first question is asking us to calculate what is the probability of the event that the function random variable function value is smaller than 0.5. This is actually the definition of the CDF function. This is equal to fx 0.5. Fx 0.5. So what we need to do next is just to observe the CDF function and pick up the 0.5 as input parameter. 0.5 is given here, and the corresponding CDF function value is at here. So we can just substitute this 0.5 into this calculation to derive the result, which is 1 plus 0.5 over 2 is 0.75. So in other words, this point is 0.75. Okay, the first part is done. Let's move on to the second part. What is the probability that the random variable x is greater than -1? So actually, we have expanded this question before, so we just use that way to solve that. So this is equal to 1 minus the probability that the x value is smaller or equal to 91, which is equal to 1 minus. The second part is the definition of the CDF function with -1 as the parameter. Now in this case here, what we need to do next is to determine the value for this CDF function when the input is -1. Okay, at the 91 point, at this point, the function value can be derived from this condition. And we know the result is 0.5. So this result is 1 minus 0.5 equals 0.5. So result is 0.5. Okay, now let's move on to introduce the second two, which is the probability distribution function, or you can call that as PDF in short. The notation for the PDF function is similar to that of the CDF function, but we don't use the capital F anymore. We are using lower f for this probability distribution function, and followed by the name of the random variable. So this means we want to evaluate the probability distribution function PDF for the random variable capital X. So the PDF function is defined as the change rate of the corresponding CDF function for the same random variable. The definition is pretty simple, but the important thing for PDF is to understand the relationship to the CDF function. So for this case, I think it would be better to use an analog example to explain the details. Let's recall, in your high school or in the first year bachelor program, you must have studied the motion of some object. For example, I got a small box, and you put that on a surface, and this small box is moving to the right. And within a small time interval, so we assume that is delta t interval, the traveling distance of this small box is delta s. So in other words, within the delta t time interval, this small box is moved to a new position, and the change of the position is delta s within the time interval delta t. So based on these conditions, we can write down the average velocity of this package within this interval is v bar. So average velocity is equal to the delta s over delta t. So very simple one. If the time interval is very small, approaching to 0, so we can use ds to dt to denote this small time interval. Correspondingly, the delta s will be changed to ds. By using the ds and dt, so the velocity or instantaneous velocity of the package at the time t can be evaluated as the ratio between ds and dt. This relationship between the so-called velocity and displacement is so similar to our definition to the PDF function. So these two have the same format between each other, and the meanings behind these two formulas are similar as well. We said the velocity is a measurement to the displacement of the package within a very small time interval dt. In other words, the velocity is the change rate of the position of the package within a small time interval. So by using the same idea regarding this PDF function here, the PDF function of a random variable capital X is the change rate of the CDF function with respect to the value lower x. Get it? There are a couple of things we need to notice. First of all, the PDF function value doesn't mean the probability of this random variable at a particular position. So we use the analog example again. So regarding this velocity and displacement example, let's assume this curve is for the velocity of this package. So let's say we have such curve for this velocity. At a particular time t1, we will be able to find what is the what is the value of the velocity at this moment. We call this point as v t1. So in such case, can we say vt1 is actually the displacement of this package at the moment t1? We definitely cannot say it, because this velocity is the change rate of the displacement of the package at that particular moment, but not the displacement at all. So these two things are different. Similarly, if we say we got a curve, x is the horizontal axis, and we want to draw the PDF of the random variable capital X, we assume the shape of the PDF function curve looks like this. At a particular x1 value, we are finding f(x(x1). Then can we say this f(x(x1) is just the CDF function value? The answer is no, for the same reason. So that means a single point on the PDF function curve is not indicating a probability. Next point, so please be careful when the CDF function f(x(x) has discontinuities. If the CDF function has discontinuities, we will not be able to conduct the differentiation calculation to derive the PDF function. That will be the trouble. Okay. Finally, the PDF term, the probability distribution function, is a valid term only for continuous random variables. If we got discrete type random variables, normally we call that as the probability mass function. So we have another set of the mathematical thing for the PMF, the probability mass function. We talk about later. Okay. The concept of the PDF function, it was not very easy. So we have known it. The troublesome knowledge regarding the PDF is about the relationship with the CDF function. From the definition of the PDF function, we have already known. So PDF is the differentiation of the CDF function. If we move the dx from the right-hand side to the left-hand side, we can derive a similar relationship like this. But this new equation can help us to understand the relationship between the CDF and the PDF very well. On the right-hand side of this new equation, we got a term d capital Fx. This means a small change of the CDF value. On the left-hand side, we got a product between the the PDF function with a small dx change. Now let's just graphically see these two components. In the CDF curve, this is the CDF curve for the random variable capital X. The small change dfx is the change of the CDF function value when the parameter x is changed within dx. So this is a small dx change. Okay. But this small change, you can see the small green color segment shown here. This small segment in the CDF function curve is equal to the left-hand side, the product between the PDF and the dx. Dx remains same in the PDF curve, so this is okay, doesn't change. The CDF function value within the dx is the height of the PDF function curve, which is fxx. But now we are trying to determine the product between the PDF with dx. So in other words, in the PDF curve here, we are calculating the area of the small section defined by dx and the PDF curve. Or in other words, this small green color column is indicating that area. This area is equal to this small segment in the CDF. Now, actually, we can just do a quick summary. A small segment in CDF is equal to the area of the section defined by the small dx with the PDF curve. Okay, so this is the relationship between the CDF and PDF. Some important properties regarding the PDF function are given in the next several slides. The first one, is not new anymore. So we have already known the principle of that. So this is that new formula we derived by moving the dx from the right-hand side to left-hand side. So this is okay. And then the dfxx, we mentioned that is a small change of the CDF function curve. Change means difference. That means the change from is x plus dx position minus the fx x. So regarding the horizontal axis, we are changing from x to x plus dx. The small change is dx, which is shown in this section. The corresponding change of the CDF function values is just the difference between this term and this term. But when we discuss the CDF function, we have already known such kind of difference between the CDF function values is indicating the probability that the random variable x value fall into these two small ranges between x and x plus dx. Okay, and this thing is equal to, if you will link this one to the PDF thing, that's equal to fxx dx. Or in other words, we said fxx, so this PDF function cannot be used to represent the probabilities, but we can use the fxx multiple dx to represent the probability that the random variable capital X fall into x and x plus dx range. Using the same idea here, in the next property, we can derive one more property here. So next one, we are saying negative infinity to positive infinity fxx dx equal to 1. But what is 1? 1 is actually equal to fx positive infinity minus the CDF function when the input is negative infinity. That is because this value is 1, this value is 0. So 1 minus 0 is 1. Of course, it's true. In other words, we are using this integration to evaluate what is the probability that the random variable value fall into negative infinity to positive infinity, this range. Of course, the result is 1 because the random variable value must fall into negative infinity to positive infinity. So this is actually calculating what is the probability of this relationship. The same thing. Okay, so this probability can be calculated using this formula through the PDF function. But mathematically, what we are doing here, so actually, first of all, we need to identify the PDF curve, which is fxx. So this curve is indicated as purple curve in the PDF function graph. And then what we are doing is to do the integration with respect to x from negative infinity to positive infinity. In other words, in this graph, we are calculating the area of the section under the PDF curve from negative infinity to positive infinity. Okay, now I have linked the CDF thing and PDF thing together and help us to understand which part in the CDF, a small segment, for example, mapped to what part in the PDF curve, which should be a small section defined by the same region as that in the CDF function. Okay. Next part, actually same story. We just changed the x values, the parameter values. Okay. In this property here, we want to determine what is the fx x1, for example. But the fx(x1) is equal to fx(x1) minus 0, which is actually the fx1 minus fx negative infinity. By doing this way, we can translate this CDF function values difference to the calculation of the area in the PDF function curve, because this is equal to the probability that the random variable capital X fall into negative infinity up to x1. This is equal to the calculation of the area from the same region, so negative infinity up to x1 in the PDF curve. So this calculation is shown in this PDF curve. You can see this green color section is indicating the area under the PDF curve from negative infinity up to x1. Okay, this is the property of the PDF function. Next one, to say the truth, exactly same story. We change the region again. In this case, we want to evaluate what is the fx(x2) minus fx(x1). So again, the difference between two CDF function values. This is actually evaluating the probability that the random variable capital X fall into x1 to x2 region, which can be calculated as the area of the section defined or under the curve of the PDF from the x1 to x2. In this slide, the bottom two rows of graphs are just showing you this procedure. So how we derive this result. So I think that's really easy. So I leave that to you. Okay. Now let's see another type of the PDF. In other words, for the discrete type random variables, we have the similar idea. We call that as PMF, the probability mass function. Okay. So if a random variable is discrete, so in other words, the values are countable. First of all, let's have the PMF first. Okay, we don't have the PDF function for discrete type random variables. We only have the probability mass function for them. The definition of the PMF function is given here. So at some particular points, xi, the PMF function value is the probability that the random variable x value is equal to that xi value. But at other points, the probability that the random variable x value is equal to 0, then the PMF value at that point is equal to 0. Okay, this idea is defined here. Okay, and at the bottom of the slide, you can see the example. This example is coming again from that rolling dice game. The horizontal axis is indicating that possible values of the random variable. We mentioned the bonus money, $100, $200, again, until reaching $600. They are used as the countable values of the random variable. And at a particular point, for example, 100, the height of the impulse is indicating the probability that the random variable x, the bonus money, of course, this value is equal to 100. So from that table, we have derived the probability for this case is 1/6. So the height is 1/6. So for this simple example, when the x equal to 200, 300, up to 600, the probabilities remain same to be 1/6. So you can see in this PMF curve, for this discrete type random variable, we have 6 purple color discrete lines or impulses. This is a PMF curve, the probability mass function curve for discrete random variable. Correspondingly, the CDF, the cumulative distribution function for such discrete type random variable, must be stepwise discontinuous. This means when we try to plot or sketch the CDF function curve for discrete type random variable, the style of the curve will not be same as that of the continuous random variable. You will not be able to see a smooth continuous function curve from negative infinity to positive infinity. The style of the CDF for discrete type random variable looks like the steps, level by level, going up. And between any two adjacent levels, there must be a sudden jump. We call that a discontinuity in the curve. This is because the change of the PMF function is discontinuous. When you use the information content in the PMF function to accumulate them together to plot out the CDF function, between any two impulses in the PMF curve, there are a small empty section. This empty section will not result in any change of the CDF function curve. For example, here, let's clear up this graph and we can show this into you. For example, we want to produce a CDF function from the PMF function curve. So we start from negative infinity and go through the whole x-axis. So from negative infinity up to 100, we got no impulses at all. So the CDF function must be flat at 0 because you are not accumulating anything. There's nothing. Once we reach x equal to 100 point, in the PMF, we got the first pulse. The height is 1/6. So correspondingly, in the CDF function, at x equal to 100 this point, so the curve suddenly changed to 1/6 because we have to add up this x equal to 100 impulse into the CDF. Then at 100, we are moving to 1/6. Starting from x equal to 100 up to the next step, which is x equal to 200. Between 100 and 200, there's nothing in the PMF. It's just totally flat, which is 0. Then we'll do the accumulation. So to add up these things together. So between 100 and 200, there's nothing. So this 1/6 point remains at the same level because you are adding up 0 to it until reaching 200. Once you reach the 200 point in the PMF, you are reaching the second impulse. At this point, the second impulse will be added on the top of what you have in the CDF. So we had 1/6 before reaching 200, and at 200 point, we need to add another 1/6 on top of it. So the level is suddenly changed to 2/6 when the x equal to 200. And then again, remains the same for a small interval before reaching 300. After reaching 300, one more 1/6 is added on top. So the CDF curve suddenly changed to 3/6. So this procedure is repeated again and again and again until reaching the very last impulse, which is increased to 1. In other words, 6/6, and then remains flat until infinity. So this is how we produce the CDF function from the PDF method. This is how we derive the CDF function curve from the PMF function of discrete random variable. Now, let's have a look at one example. A random variable x has a PDF as follows. So please evaluate the value of the constant c. In this question here, I suppose this random variable x is a continuous type random variable, because when we come to the small region between -1 to 1, this fx curve looks like a continuous curve, not discrete case. Because of that, I assume this random variable x is a continuous type random variable. Now, for this continuous type random variable x, how can we solve the constant c? So we need to use the properties we learned regarding the continuous type random variable. Here, we are using this property. So fx positive infinity minus fx negative infinity is equal to 1 minus 0, of course, so equal to 1. This is pretty straightforward. But in the meantime, we mentioned such CDF function value difference can also be represented by the integration of the PDF function from the same interval, so negative infinity to positive infinity. So this is equal to, for this particular case, because we have non-zero value for this PDF function only between -1 to 1 decimal region. So we can change the integration boundary from -1 to 1 and then put c by 1 minus x squared dx as the PDF function within this region. And this integration will be equal to 1. So in other words, we can write integration -1 to 1 c by 1 minus x squared dx equals 1. Then we can just solve it. C multiple -1 to 1 minus x squared dx equal to 1, or c multiple x minus x cubic over 3 minus 1 to 1 equal to 1. So I need more space. Keep going here. So c multiple. So when the x is 1, so 1 minus 1 over 3 minus -1 minus -1 over 3 equal to 1. So this gives us c multiple 2 over 3. This is just cancelled. So minus negative 2 over 3 equal to 1. So c by 4 over 3 is 1. So this gives us c equal to 3 over 4. Then you solved. C is 3 over 4. Okay, finish. Now let's move on to the next topic. From this slide onward, we are going to introduce some extensions to what we have learned. The first concept we are going to introduce here is called conditional distribution function. So please be reminded, we do not call this conditional distribution function as CDF, because the CDF term is dedicated for the cumulative distribution function. This conditional distribution function is very similar to the cumulative distribution function. They have the same notation, so capital F. And the parameter is lower x, so remains same as well. The only difference in the conditional distribution function is the vertical bar and this letter M. This vertical bar means conditioned on or subject to, and this M is some observation or condition you have already known. So in other words, the conditional distribution function is evaluating the cumulative distribution function of a random variable when some condition is known. This condition and this random variable generally should have some relationship So the condition can affect the random variable. A good example is if we define the random variable as our final exam mark. E1 to M could be the format of exam. So for some students, the format of exam could affect the performance, the mark of the final exam. So that means these two things, the event M, the condition M, and the random variable X have some interactions. One can affect the other one, okay? If I do not give you any information regarding the format of the final exam, that means you do not know the M. So if you want to estimate or model your final exam performance, so you are actually evaluating fx, and that curve may look like this. So x and 0 mark is given here, 100 mark is given here. But because this is about CDF function for this random variable, so its curve must be between 0 and 1. And the shape of the curve may like this. Of course, depends on your performance. Okay, this is the CDF function for the random variable x. But if I give you information regarding M, the format of the exam are just all questions. Maybe some students like this format, so the performance will be improved. In such case, when you re-evaluate the performance of your final exam, you are evaluating the conditional distribution function of it. So fxx x subject to M equals M2, all multiple choice questions. And based on this fact, based on this condition, so the curve, the CDF curve for the random variable x will be changed to maybe something like that. Okay, so this is just an example. Next concept is the conditional density function. I think this idea is so similar between the to the relationship between the PDF function and CDF function. So remember PDF function fx is the change rate of the corresponding CDF function. Such relationship is reused here to derive the conditional density function from the conditional distribution function. So I don't want to just spend time to just introduce the details again. So we have already known that. Okay, let's move on to the next slide. In this slide, we are going to study another three concepts. First one, marginal distribution function. In this function here, we want to evaluate what is the PDF of the random variable x. But the tricky point for this concept is we have the event A, which can affect the random variable capital X. Just like X and A. This is the exam. A is just a format. This A contains two sub events. One, all questions. A2, all calculation questions. Now, if I just want to evaluate what will be the performance of the exam, so I can evaluate the PDF of the random variable x. But because both A1 and A2, these two events can affect my performance, so I have to consider what will be the PDF of my final exam if the final exam contains all multiple choice questions.
And also you have to consider what is the PDF of the final exam when they are all calculation questions. The summation of these two estimations comprises your final exam performance. But in this case here, you have to also consider what are the probabilities of these two events separately between A1 and A2. So here, much of A1, A2 to consider what are the likelihood that this event happens. For example, A1, 10%. So there's only 10% I can give all multiple choice questions in the exam. Based on this 10%, what will be your performance? And then 90%, I give you all calculation questions. And based on this truth, what will be your performance? Then the summation of them make up the final performance of the final exam. Okay. Okay, this first concept. So marginal distribution function, and let's move on to the next one. The total probability theorem. So actually, this idea is so similar to the marginal distribution function, a little bit different. Okay, so let's just find some space and keep writing. Regarding the total probability theorem here, the target is to evaluate what is the probability of the event A. So this is our target. But let's have this part first, which is P A subject on X, X, F, X, X, B. This is used to evaluate what is the probability of the event A when the random variable capital X is equal to a given value X. The next term here can be translated to EFX. So this concept is used to in the interaction of the PDF function, right? And this small change of the CDF function value is actually, I think this is the probability that the random variable X fall into X, and X plus dx small region. But if the dx is very, very small, approaching to 0, so this stuff can be approximated to the probability that X is equal to X. Now we can use the final result to replace this. So what we have here is this stuff. Okay. Now this result is pretty good because you can see this is a very typical format for calculating the joint probability. So this is actually equal to the joint probability of A event and X go to the lower X event. That means what is the probability that event A happens and X random equal to the X point happens? But you know, the X is a continuous random variable. In such case, we are doing the integration. This is joint probability with respect to X from infinity to plus infinity. That means we need to consider all the possible points of X so that the effect of the X can be eliminated. The remaining thing is just the probability of the event A only. Like that. Okay, so this is done now. Very last one, the Bayes theorem. This is one important theorem to, I think, part 3 of chapter 1. And we may have some questions using this theorem in the class S1 and also in the final exam. Okay, but this part involves some mathematical inductions. So if I can't finish that in the lecture, in the video, so you can just go through that by yourself. It should be very simple. Okay, so for this basis, so how can we do that? I think for solving for deriving the basis theorem, the good way is to start from a joint probability, which is P A. Random variable x is between x plus dx. This joint probability can be translated into two different formats. First format, so we are treating A as event A as subject to the second term. By using that hint we mentioned before, so this should be multiple the probability of the condition, which is x plus dx. This is the first format. Another format is similar to this one because the two terms inside of this joint probability are interchangeable. So we can just write down another thing which is similar. This second term, that becomes first term, then PA here. Now in this part, let's have this term. What is the probability that the value of the random variable capital X fall into X and X plus dx? This term is actually, so actually we have so that this is the probability that X fall into this region. That should be dfx. Or you can see that to be the fxx dx. And similarly, for the first term here, this is actually fxx subject to A, then dx. Now we can rearrange the whole equation to be like this. Cancel some common terms to derive the next step. So we keep this one at one side of the equation. So fx on A is equal to PA at the bottom of the other side. And on top, we have PA I x here. Now, this condition, we have solved that before, right? So this condition can be translated to that x equal to x when dx is very small, right? So x then PA. So this final result is so-called the Bayes theorem. Okay, so I don't want you to memorize the mathematical inductions. Knowing this final result should be sufficient for this theorem, but there are a couple things you need to know how to derive that. For example, we say dfxx is equal to fxx by dx. So this is not new thing in this Bayes theorem. We have introduced this one before. You need to understand this one. Okay. So let's move on to the next slide. the function of a random variable. In this part, I'm going to use two examples to help you to understand this new concept. This part will be important, okay? In this part, we assume there are two random variables, y and x. And the relationship between these two random variables are clear and deterministic. So the relationship is y equals gx. And we have already been given the CDF function of the x. So fxx is known. The question is, what is the CDF function of the y? So if you just read the unit reader, you can find this formula easily. But please make sure you really understand how to use this knowledge to solve the question. So I'm trying to use my explanation to help you to understand this idea, okay? So we said the relationship between the y value and x value are clear and deterministic. So in this small graph, you can see here, the horizontal axis is a random variable x, and the vertical axis is a random variable y here. The relationship between x value and the y value is defined by this slope line. This is just example. Okay, this line y equal to gx is defining the relationship between random variable x and random variable y here. And we want to determine what is the CDF function of the random variable y. Based on definition of the CDF function, this can be translated to the calculation of the probability of the range y random variable smaller or equal to the given parameter y here. Now we assume this given parameter y is at this point. Now this point is along the y-axis, so this is okay. And the event y is smaller or equal to this given parameter y is indicated by this blue segment on the graph. So from negative infinity up to this lower y point, this is the region. So what is the probability that the random variable capital Y fall into this blue segment? But because we are having that deterministic relationship between y value and x value based on the gx function, so all the points on this blue segment can be mapped to the corresponding x-axis point through this gx point. For example, if you are talking about this point, I just give the name y1, for example. So through this gx function, I'm able to convert that or map it to the corresponding x1 value. So what is the x1 value? This x1 value is equal to inverse g by 1. Okay, so this is the relationships. We are evaluating what is the probability that random variable y fall into this blue segment along the y-axis. This relationship can be translated, so based on this example, of course, the probability that the x random variable fall into negative infinity up to x point. So where is the x point? So let's remove this part, okay? This x point corresponding to the y point. In other words, this evaluation is regarding the evaluation of the probability that the random variable x fall into negative infinity up to this x point. The same thing. But here, now finish it. What is this probability? This format is so familiar to us. It's actually the CDF function of the random variable x by using the x as the parameter. So in other words, so far we can say the CDF function y is equal to the CDF function of x. You need to notice, actually, this result is not good enough because you want to solve what is the CDF function of the y. In this calculation, the lower y is used as a parameter. But up to this step, you don't have this parameter y here. Instead, you are using the parameter x. So you need to go one more step so that the parameters used in these two functions are compatible between each other. So the very last step is fx. So how to convert the x to the y equivalently? The gx function. That's g of the then finish. I think this is the first part for the function of random variable. Next one, regarding the PDF. Idea is similar, but there are some tricky steps. So in this question here, same thing, we know the relationship between two random variables, y and x, such as gx, y equals to 2gx, and the PDF fxx is known. What is the PDF of y? So for this question here, I solve it by making the equal probabilities between these two random variables. Now you can see, same thing. The horizontal axis in the graph is the random variable x. The vertical axis is the random variable y here. And the relationship between these two random variables is the gx. So all the conditions are given here. And I want to define a small step along the x-axis. So I call that as a dx. This small dx is mapped to the y-axis through the gx function correspondingly. Then I derive dy here. So remember I said, based on this y equal to gx relationship, so f y are the same if the y and the x are corresponding between each other. And this small increase of the theta function should be same as well. Such kind of thing can be converted to fxx dx fy y. In this case here, dx dx dy have already been given in the graph. fxx is known. Our target to solve what is the fyy. So let's just rearrange that. So we got fyy. We just keep that I at one side of the equation. Suppose we move the dy to the other side. So we got fxx dx over y, which is equal to fxx multiple 1 over. So we just turn this fraction upside down. It's dy over dx. Actually, at the bottom of function, dy over dx is the derivative of y with respect to x. And this is also translated to because y equal to gx, this function is given. So that gives us gx derivative. We must use y as parameter, not x. So this x must be converted to fx gy inverse. Then multiply for gx derivative. Okay, and there's one more thing we need to notice. So regarding the sign of this derivative, this derivative of the gx function could give you a negative sign. It is decreasing. But because we are actually calculating the equality of the probabilities, so we do not consider the negative sign. So here we put the absolute value around it. Okay, so this is just the main idea regarding the function of random variables. We are dividing this topic into two parts. One is for the CDI function, one is for the PDI function. Okay. Okay, now let's quickly go through the remaining slides. We don't have too much left. Some important operations to the random variable or the functions involving random variables. First of all, expectation of a function g which involves a random variable x as the input parameter. So the expression of gx provides a measure of the average or mean behavior of the gx. We are using the calculator e to denote the expectation operation, and the gx is put inside of this operation. That means we want to evaluate the expectation of gx function to know the mean of this function. Okay, the calculation of this one is just like a template. Okay, so the expectation operation is corresponding to the integration something multiple the PDF of the random variable dx. So this is template for the expectation operation. No matter what expectation you want to calculate, this inside the integration. So multiple this function with the PDF of the random variable, and then do the integration from negative infinity to positive infinity. Do that. And next one, the nth moment. We are using the mn to denote moment. N means odd number, so mn is used to denote the nth moment of the x. This is actually an expectation operation to x power to n. The remaining steps are pretty easy. It's just using the regular way to calculate the expectation. Put the xn inside of integration, multiple with the PDF of the random variable, then finish integration. You got the nth moment. In our unit, typically we focus on a special case where the n is equal to 1. When the n equal to 1, this m1 is equal to the expectation of x power to 1 only. X power to 1 is just the x itself. So in other words, we are calculating the expectation of the random variable itself, and is equal to negative infinity positive infinity integration x by fxx dx. The result derived is called the mean of this random variable. Okay, and next one, a new concept, nth central moment. Central moment. Central moment is denoted by the c, letter c, lower c. The nth central moment is denoted by Cn. Is equal to actually another expectation operation. Inside of the equation, you got this term x minus this ex is the expectation of random variable x. In other words, this is the mean of x. So this is actually equal to the expectation of x random variable minus the mean of this random variable. Normally we are using mu x to denote mean of the x. and then try to n and close bracket. So this is the way we calculate the nth moment. We need to just pay extra attention when the n equal to 2. When the n equal to 2, we got the second central moment, which is the C2, equals expectation of random variable x minus the mean of the random variable x and square the difference and close bracket. This special case is also called variance. In other words, when the order number is 2, so the second order central moment is called variance of the random variable. Okay, and we have a special notation for that. Normally, it's just a sigma x square for this one. This is called variance. And this kind of variance calculation can be expanded. So inside of the expectation operation is x minus mu x squared. So x minus mu x squared is actually x squared minus 2 mu x by x random variable plus mu x squared. But you know, the expectation doesn't have any effect to the constants. But the mean value of the random variable is just a constant. So this can be converted to e x squared minus 2 mu x e random variable x plus mu x squared. This part, the expression of the random variable x is just actually the mu x. So this term is then converted to 2 mu x squared. Then we can keep writing here, that's equal to e x variable squared minus 2 mu x squared plus mu x squared, which is equal to the division of the random variable x squared minus mu x. That result is also shown here. Sorry for the massive writing, but I think this can help you to understand what you are doing. So these operations like the expectation, the mean, the variance will be used many times. So today we just push this concept to you, and I hope you can just go through them and make sure you can distinguish which one is which and how to conduct these operations.
Okay, everyone, let's move to the very last part of this lecture. In this part, we are going to introduce 6 typical distributions. Out of these 6 distributions, the first 3 of them are continuous type random variable distributions, and the later 3 are discrete type random variable distributions. Let's go through them one by one. For some of them, I'm to show you how to calculate their mean value, the variance of them, how to determine the CDF from the PDF. So something like that should be pretty simple, just using the knowledge we have learned from the previous part of this lecture. The first distribution we are going to introduce is the uniformly distributed random variable. This is also a random variable, but its pattern is very special. So for this particular pattern random variable, we call that as uniformly distributed random variables. Let's have a look at what is the feature of such type of random variable. First of all, uniformly distributed random variable is one of the continuous type random variables. is continuous. And is PDF, the probability distribution function, has a very special pattern. You can see here in this page, maximize window, the PDF function of the uniform distribution is given here. The random variable is x. Its PDF function is divided into two parts. A and B are constants. The first part is defined within A and B, this small region, and all other values except the AB region will be treated to the other part. So within AB region, is PDF is a constant because B is constant, A is constant. So 1 over B minus A, of course, is a constant. Okay, so this is a constant. That means if we draw the PDF of this uniformly distributed random variable, A is here, B is here, between A and B, we got a constant value for this PDF of this random variable. And out of this AB region, they are all zeros. They're all zeros, and non-zero between A and B. So if you see the pattern of the PDF curve of a random variable looks like this, you can see this random variable should be a uniformly distributed random variable. But what are good things for this kind of random variable? Okay, first of all, let's have a look at the CDF function for such case. CDF function we said is a function. So fx is x's name of random variable using x as the parameter. And we determine the CDF function for a random variable as the integration from negative infinity up to the x point. Then integration to the PDF of it, then dx. In this case, because for this particular type of the random variable, so we got 0 values before reaching the A point. So we can change this to from A to X, f x dx. Of course, in this case, we assume x is smaller than or equal to b, smaller than or equal to b. In this case, what we got is A to x, and then for the fx, we just copy down the constant 1 over b minus a, then dx is equal to 1 over b minus a multiple x minus a, which gives us x minus a divided by b minus a. This is a linear increasing curve. Okay, and how about if the x is greater than b? This condition is changed. So this case is changed to equal to a to b f x dx plus, because x is greater than b, from b to x, and then f x dx. Within a to b, you can just copy down 1 over b minus a dx plus. So from b to x, because currently the x value has been higher than b, so when the x is higher than b, we go back to fx curve, the PDF curve here. You can see if the x is higher than b, the value of the PDF function curve will be 0. So this part will be 0. So this gives us b minus a over b minus a, which is equal to 1. Okay, so how about if the x is smaller than a? So now this is the I forgot to write down the condition. This condition is x is greater than b. Okay, so we got this result. This is given here. For the x smaller than a case, so I don't want to do the calculation again. So you can just try it by yourself. The result is 0. Now, after you finish all these steps, you can find the CDF function curve for uniformly distributed random variable will be like this. It's a CDF function curve. X, A is here, B is here. So I'm using a green pen here. So before reaching A, we got constantly 0. And between A and B, we got a linearly increasing curve. The endpoint will be 1. Sorry. The endpoint will be 1. Why the endpoint is 1? See here. If this x is equal to b, the result will be 1. Okay? And then from b forward, you got a constant flat out curve, which is equal to 1. Okay, now we have already known the PDF and CDF for uniformly distributed random variable, and the pattern are very special. Okay. Now let's clean the board and we keep going discussion. Okay. Okay, now let's keep going. But knowing the PDF and CDF are not sufficient, because we also want to know what is the mean and the variance of the random variable. Let's just keep using the same example and we just try to determine what is the mean of this uniformly distributed random variable. The mean of the random variable. Let's use mu to denote the mean of random variable x. Or if you want, you can use the expectation operator to the x to denote the mean as well. So same thing. Okay. Now we want to calculate the mean of the x, which is a uniformly distributed random variable that's equal to the expectation to the x random variable. We mentioned the expectation operator is just like a template. Put the integration f x x t dx. This is just a template from negative infinity to positive infinity. And then no matter what you have inside of the expectation operator, just move it into the template. X is changed to x. If you got the other thing, just change it. Okay, just move that to the integration. And then we want to just calculate this integration. So what we have is negative infinity to positive infinity x by the fx x dx. But don't forget, for this particular uniformly distributed random variable, is PDF is very special. Just have the values between a and b, and all zeros out of the AB region. So between a and b, the height is 1 over b minus a. So we just use this knowledge. We can get between a and b, we got x over b minus a dx, which is equal to, we can move the 1 over b minus a out. So 1 over b minus a integration x dx, which is equal to 1 over b minus a half x squared before AB, between AB, which is b squared minus a squared over 2, then 1 over b minus a. This can be further simplified. So b squared minus a squared is b minus a by b plus a, and b minus a can be used to cancel another b minus a. So these two things are gone. Result is b plus a over 2. Now let's have a look here. Where is a plus b over 2? If you think a is here, b is here, the b plus a over 2 is just the midpoint between AB region. This is the mu value of this random variable. Of course, this makes sense because this is uniformly distributed signal. Okay, this is how we calculate the mean of a uniformly distributed random variable. For the variance, I know you may have already known that, but let's try it again to make sure everybody understood how to do the calculations. Okay, so next one, I want to determine what is variance for this x random variable. Again, you may write the expectation format for this variance term. This is equal to expectation of the random variable x minus the mean value of this random variable and squared, because we mentioned the variance is actually the second order central moment. Again, expectation is the integration of something multiple the PDF of this random variable dx from the negative infinity to positive infinity. Now, no matter what you have here, copy that into the integration. So you got x minus mu x squared. Again, because of the special pattern of the PDF for this uniformly distributed random variable, so you can change the boundary of the integration to a and b. Then x minus mu x squared divided by b minus a dx. We have solved the mu x, which is b plus a over 2. So we can just rewrite this integration to AB region x minus b plus a over 2 square dx. And I don't want to spend my time to finish calculation. You can do it by yourself. This is our first way to determine the variance of the random variable. And actually, we have another way to solve that. We can just stop our calculation to this way. We can just simplify this expectation equation first. We said this expectation of x minus mu x squared can be converted to ex squared. This x is a random variable, okay? Minus the square of the mean of this random variable. This is equal to ex squared minus, for this mean, we have solved that, which is b plus a over 2. You just need to square it. Regarding this term here, is equal to integration negative infinity to positive infinity x squared, and then the PDF of this random variable, which is 1 over b minus a dx minus half b plus a squared. And again, simplify it. I think you can do that by yourself. I just quickly write them down, a and b. Right. So a and b, and then x squared dx minus half b plus a squared equals 1 over b minus a, and then x cubic over 3, a and b minus half a plus b squared. And then you can finish your remaining steps. This should be pretty easy. Okay, the reason I show you these two different approaches, it just gave you the idea that we can use different ways to calculate the expectation. You can just pick which one is easier for you. Okay, so I didn't finish the full calculation, but we can just see the result. So the variance for uniformly distributed random variable is given here. Okay, I think these stuff are pretty easy but important, because you will face some similar type of the random variables in your future study. Okay. Okay, let's move on to next tab. The second continuous tab, distribution. So this one is called normal or Gaussian distribution. And the pattern for this type of the random variable is also special. You can see this is actually exponential function. And in front of the exponential function, we got a small coefficient. This coefficient is related to the variance of this random variable. In the meantime, the power number of the exponential function is also related to the variance of this random variable. In addition, this mu here is actually the mean value of the random variable x here. Okay, if you see a pattern of the PDF function of a random variable like this, this is a normal distribution random variable. And for such normal distribution random variable, its mean is mu, its variance is sigma squared. Actually, these two values can be read directly from this PDF function curve or the PDF function mathematical expression. Once you know the PDF function of a normal distribution random variable, we should try our best to derive the CDF function. And of course, we are using the same idea to calculate the CDF function. But after you reach this step, you may find you can't move any further. The reason is, for such kind of integration, we do not have a closed form solution to it. So in other words, we will not be able to use a formula to determine the values of the CDF function directly. Then for such kind of formula, we have to use a table which mapping the input parameter to the CDF function to indicate what is the result of the CDF function curve. Okay, so for this case here, I will not request you to calculate the CDF function curve or values by calculation. I will just ask you to check tables. Okay. But for the normal distribution, with better to understand, when should we use the normal distribution? This will be used to describe the statistical behavior of most physical phenomena, like the heat transfer or the motion of small particles. So all this stuff can be described by such kind of distribution. Okay. Okay, the very last type of the distribution, we call that as exponential distribution. Normally, for discrete arrival events, the waiting time distribution are following such kind of patterns. For example, we assume you have a small bank, and in the early morning, you open the door to the customers, and the customers randomly come to your bank one by one. So, of course, the arrival events of customers are individual events. So if we draw a timeline, and at different time instance, the customers come into your bank independently, and then the waiting time or arrival time, so the time interval between any two customers coming into your bank is denoted to be T1, T2. This T1 is not the exact arrival time, is the time interval between two arrivals. Okay, so the inter-arrival time, for example, such T1, T2, T3, these time intervals can be treated to be a variable, random variable, capital T. This capital T is following the exponential distribution. Okay, so this is just the idea of this concept. But what is the feature of this exponentially distributed random variable? Okay, see here, we have got its PDF looks like this. The shape of the PDF curve will be like, so I think about using X as the x-axis, right? And this is the PDF of it. The curve of the exponentially distributed random variable looks like this shape. Is an exponential function. So you can see here is one exponential function. So when the x is 0, when this x is 0, e power to 0 is 1. So we reach the peak value, which is lambda, and then decays quickly to 0 when the x going up. So just whole story. And then using the same way we used in the calculation of the uniformly distributed random variable, you can do the same thing here to calculate its CDI function, its mean, its variance. It should be very simple. So I don't just do them again. So you can try them out by yourself. So we need to understand, we need to know by the end, for this type of distribution, the mean value of the random variable is 1 over lambda, and the variance is 1 over lambda squared. And its CDF function is 1 minus e power to negative lambda x1. Very easy calculation. I believe you can do that by yourself. But if you have a question or trouble, let me know, please. Okay. Now we have done the discussion regarding 3 continuous distributions. What I want to remind you to do is you need to understand what are the features of this random distributions, and in what kind of situations you need to use them. And then you must be able to know how to calculate the mean value, the variance, and the CDI function. Okay. Now let's move on to the next part, the 3 discrete distributions, or the distribution for 3 discrete type random variables. The first one is the Bernoulli distribution. So let's use X to denote an event of interest with 2 outcomes. So in other words, for this random variable X, it has only 2 possible outcomes, 1 or 0, 1 for success, 0 for failure. Then the Bernoulli distribution describes individual random failure events where P is the probability of success, and Q, which equal to 1 minus P, is the probability of failure. This is the PMF function of the Bernoulli distribution. It has only 2 possible values, 1 or 0. Like this. Of course, for this translation of 1 to 0 to some physical meanings or terms, it's up to you. Maybe you can define the 1 to be the head of a cone. The 0 is the tail of a cone. In the cone tossing game, it's fine. And maybe you can use the 1 to be like the light up, 0 to be the light off. That's the same thing, so it doesn't matter. But we are using the 2 numbers, 2 numerical values, 1 and 0, to represent the 2 possible outcomes. And the probability that the random variable capital X equal to 1 is P. The probability that random variable X equal to 0 is denoted by Q, which equal to 1 minus P. Look at that. So if you really want to sketch the PMF function curve for this Bernoulli distribution, it should be very simple. This is just X value. This is the PMF function of the random variable X. So it has only 2 values, 0 and 1. So the probability for 1, this height is P. And the probability for X equal to 0 is 1 minus P. Just 2 impulses, nothing else. Pretty simple one. Okay. And for the evaluation of the mean value, because in this case, because discrete type random variables, so the evaluation of the mean value is equal to the expectation of the x. So this remains same. But regarding the calculation of this discrete random variable expectation, you can't use the integration. You have to use the summation. And then x value multiple the probability that the random variable equal to this x. Of course, because you have two options, so we use xi to denote it. Xi it. I equal to, because you have two values, so from 1 to 2. So this gives us x1 multiple probability that x equal to x1 plus x2 multiple this, which equals, so x1 is 1 multiple the probability that the x equal to 1, which is actually p, plus x2 is 0 multiple 1 minus p. Result is p. So you can see we derive this mean easily. For the variance, so I don't want to do the calculation again, so it should be very easy. You may try it out by yourself. Okay. So regarding the Bernoulli distribution, first of all, we need to understand its feature because it has only two outcomes: win or fail, win or lose, success or fail. Okay, so understand this thing, and we also need to understand how to calculate the mean value, how to calculate the variance of it. And then move on to the next tab, discrete type random variable, binomial distribution. The binomial distribution comes from the Bernoulli distribution. You can see here, for this distribution, in an independent trail of n times Bernoulli experiments. In other words, this binomial distribution is a sequence of Bernoulli experiments. This P, because this is discrete type 1, so we are using PMF. For PMF, we need to count the probability that the random variable value equal to a particular xi point. So now P, the probability that x equal to k, denotes we have k times success in this n times Bernoulli experiments. Okay, so this is the case, and the PMF function of such binomial distribution is given like this. This combination indicates out of n times Bernoulli experiments, we have k times successful. So because of that, so we need to just multiply the probability of each Bernoulli experiment success power to k times successful. Multiple this times, this is the probability that we fail the Bernoulli experiment power to the time that we fail this Bernoulli experiment. Based on this PMF function, we can derive the mean value and the variance value by using the method that we introduced in the previous slide. You can try it out by yourself. Okay, the very last one, Poisson distribution. Poisson distribution is kind of related to the exponential distribution, which we mentioned in the continuous type distribution. Okay, we mentioned, remember, you got a bank and you open a door in the early morning, customers come into your bank one by one, and we are using the exponential distribution to model the inter-arrival time. Okay, this is what happened before, but now we are talking about the Poisson distribution. The Poisson distribution is described the same story, but from the other way. So here is the time. At a different time instance, different customers come into your bank. But this time, for the Poisson distribution, we are not focusing on the inter-arrival time. We are focusing on within a unit time, how many customers come into my system. This green point along the time axis is indicating the arrival time of the customers. But if we divide the time axis into a sequence of equal spaces time instance, this equal spaces time interval should be very small. Okay, so all these blue points are indicating the time ticks. Okay, equal spaced. And if we focus on within one single unit time, what is the average number that customers come into your system? This is modeled by the Poisson distribution. Okay, in other words, for Poisson distribution, we focus on the number of customers or average number of customers come into my system within a unit time. Okay, so here you can see we assume there are an average of lambda events or lambda customers over a specified region, like a time interval, whatever. And this is the modeled by the Poisson distribution. The probability of exactly k events happens over that region is given by such probability. This x here is, of course, random variable. That is the number of customers, or we can call that events generally, happened in a specified region or time interval. So this PMF is used to describe such random variable. Follow the Poisson distribution. Okay, the mu value, the mean is the lambda, and the variance is lambda squared. Okay, so again, for the discrete type distributions, we need to understand, so under what kind of situation we should use which distribution. Secondly, what are the PMF function for these distributions? By the end, we must be also able to calculate the mean value and the variance. In my lecture today, I didn't go through the calculation of all the distributions, but I think most of them should be pretty easy. I just gave you 2 examples, and you can follow the examples to finish your mining calculation by yourself. Please make sure you understand how to calculate expectation, the mean value, the variance value, all this stuff, because in our future study next week, we are going to use them to solve some questions.